Okay, how are you guys doing today? Good. Good. So last time we had a brief introduction to microcontrollers. We learned a little bit about circuits also. So today we're going to start with a quick review of what we learned last time, and then we're going to go into microcontrollers a little bit more. Today we're going to be using the basic stamp again, and we're going to be creating Morse code. All right? So that should be a lot of fun. We're also going to have a visit from the dean of our department, Trish Caldwell. She should be here in just a minute to welcome you guys. Hey, everybody, this is Trish Caldwell. She is here to just say a few words and welcome you guys to the school.
I don't know the fun stuff, this is good. But anyhow, I'm Trish Caldwell, I'm the Dean of Technical Education. But I wanted to let you know, I wanted to welcome you to technical education and to electronics technology. I frequently say that this whole area is where the magic happens. There's some pretty cool stuff happening here. And he's one of the guys who's doing a lot of it. Also wanted to let you know that it started in the fall, but we have counselors just assigned to tech ed, which is a huge change for us. We've had over the years people go to regular counselors and they do their best, but there's so many programs and they don't really know us as well as we'd like them to know. So we have two people who are assigned just to us, and they are in the technical education office, the faculty office building, which is over toward that first where the new water fountain thing is, to the right and then to the left. And you can drop in. If they aren't busy, you can talk to them then. Or you can drop in, you can go into the office and schedule, book an appointment to see them. Monday, Tuesday, Wednesday, Thursday, there's an evening and they can make the accommodations I'm sure. So I'd strongly encourage you to do that. If you're working on a certificate or a degree, as much as we love to have you here forever, I know you all want to get out and get back when you're probably working. Continue to work, get a raise and whatever it is that's going to happen. Always really good. So the more efficiently you do that, the better off you'll be. And then you can decide to come back later and take more classes. But in the meantime, they'll help you do that, and they can also help you with financial aid. So that's pretty cool too. And
do you know if they're doing visits for student education plans this semester?
Not into the classroom, probably not.
Okay.
No. But you could do the ed plans with them. That's really the goal. So you can sit. It's just one-on-one, which is handy. Because there's some glitches. So that's it. And then the Sacramento Employment Training Agency will also have a person here. Say this already. And she, I don't know if you've had anything to do with SETA, but they're more employment focused. So she'll be in our offices. She's supposed to be serving the whole campus, but we're not going to tell them about it. And she can help you with resumes and with mock interviews. If you qualify for some sort of aid, then she may be able to give you funding to help buy tools that you might need for your first job. So that's all worth checking out. And then in addition, there is the one other thing I want everyone to know about. We have a filtered water bottle station, chilled filtered water station over at the north end of, it's right next to 303 or where that restaurant is. That's a really cool thing. Anyhow, do you have any questions? Well, enjoy the semester, and as I said, you're in good hands with Jordan, and I'm sure you're going to do national stuff. Thank you. Thanks, Jordan.
Thank you. All right. Cool. So like Trish mentioned, the career counselors are excellent. They're there for you, and I highly recommend going to see them and really filling out an education plan if you get a chance. This is a goal that you set for yourself. You get to determine what it is, and it really helps to have a plan as soon as possible. That way you know where you're going and you can figure out the steps how to get there. If you get a few class is in and you change your mind, that's fine. You can always go back and change the plan. But it really helps to have a plan in place from the beginning to help you get to where you need to go. Okay? That they can help you set that up, and then once you get that, you can figure out which classes you need to reach your goals, when the best times are to take those classes, because not every class is offered every semester. Sometimes they're every other semester, things like that, so you can figure out where they are, and they can help you do all that. So it's a really, really great resource, and I highly recommend it. So, any questions about that? Okay, then let's do a quick review of what we talked about last time. Last time we talked a little bit about circuits and circuit diagrams, right? And then we also talked a little bit about programming. So we're going to review both of those things pretty quickly. So we talked about circuits. We talked about some circuit symbols. So what did this circuit symbol represent?
Battery.
A battery or a power supply. Yeah. And it had usually a positive and a negative terminal, and then some indication about what voltage it had. So that was a battery. What about this one?
Diode.
Exactly. A diode. When it's just a plain symbol like this, it's a diode. What does it become if we add this extra arrow there?
LED.
An LED. Right? The arrow is supposed to represent light, so this is a light emitting diode. Perfect. What about this one? A resistor, exactly. So what does a battery do in a circuit?
Supply power.
Yeah, it supplies power. We haven't gone into a lot of detail, but exactly, it supplies power. It really is the thing that pushes the electricity around a circuit. If there's a battery, then it causes the electricity to move from the positive terminal to the negative terminal through your circuit. If there's no battery, there's nothing pushing the electricity around, so it doesn't flow and your circuit doesn't do anything, right? What about a diode? What does a diode do?
It's only one way.
Yeah, it's a one-way valve for electricity. So if you put it in one orientation, it allows the electricity to flow through. If you swap it around and reverse it, then it blocks the electricity from flowing. If you have electricity flowing through an LED, does the light go on or not?
Yes.
It does go on, exactly. And what about if you turn it around and it blocks the electricity? No light, exactly. So that's why you have to put the LED in the correct orientation, because you want the light to go on, so you want the electricity to flow through. What about a resistor? What does a resistor do?
Reduce the amperage.
Yeah, it reduces current. It resists the flow of electricity. We said that there are different ratings for resistors. So last time we looked at 470 ohm resistors. And we said that the bigger the resistor was, the more it resisted the flow of electricity. So the less electricity would flow when you have a bigger resistor, right? If you have a smaller resistor, it's less resistance, it allows more electricity to flow, okay? And why would we want to put a resistor in our circuit? Yeah, exactly. If we didn't have the resistor, then we'd have lots and lots of electricity flowing through, and it would heat things up too much. So then we could get burned if we touch it. It could start fires if it's touching other components. And also, it would just be using a whole lot of energy. That would run down our battery really fast. It would cost more money to supply that electricity. It's just not efficient. So that's why we use resistors. Okay? We talked about a couple of different kinds of circuits. We built a simple circuit that looked like this, right? We had a battery over here, and then we had a resistor. And what was down here? An LED. Yeah, exactly. And then it went, and the circuit wrapped back around and connected back to our battery. when we built this circuit, the LED turned on, right? And we chose the 470 ohm resistor up there. Now, if we had picked a bigger resistor, what would have happened to the brightness of the LED? It would have been dimmer, right? A bigger resistor means that there's more resistance to the flow of electricity, which means that less electricity flows. So when less electricity flows through the LED, you get less light coming out. If we picked a smaller resistor, the opposite would have happened. We would have had more electricity, so we would have had a brighter LED. Okay? If we picked a resistor that was too small, or we didn't have a resistor at all, then we'd get too much current flowing through the LED, and it might burn up or explode. And if we picked a resistor that was too big, you might not see any light coming out of the LED at all. So you have to pick a resistor that's just right. And we'll talk about how to do that later on in the semester. Okay? So any questions about circuit components that we've talked about so far, or about simple circuits? Okay. We also talked a little bit about programming last time, right? We wrote a couple of simple programs for the basic stamp, and we looked at some of the commands that were available. So we looked at a command that was high 14. What did that one do? Yeah, it turned on pin number 14. Remember, the basic stamp had these 16 pins. They were numbered 0 through 15. And we could turn each pin on or off. If we turned it on, then we got 5 volts at that pin. If we turned it off, we got 0 volts. So when we say high 14, we're telling the basic stamp that we want to create a high voltage at this particular pin. So what happened if we said low 14? Turns it off, right? High turns it on, low turns it off. If we have an LED and a resistor connected to one of these pins, then when we say high 14, that turns the LED on. If we say low 14, it turns the LED off, right? So we were able to use those two commands to turn the LED on and off. Now, what would happen if we just ran these two commands right after each other? Would we see the LED turn on at all? No, probably not, because there's no time in between these. The only time is the amount of time it takes for the computer to read one line of a program, which is almost instantaneous. So the light would turn on and then turn off immediately. We wouldn't be able to see it go on at all. So what do we need to do? What command can we use to keep the light on for a certain length of time?
Loop.
Pause. Pause, yeah. So we said pause, and then there was a number after that. So if we said pause 500, what did that mean? How many seconds would that be?
Half a second.
Half a second, right? So this is 500 milliseconds. There are 1,000 milliseconds in 1 second. So 500 is half a second. So if we had said pause 2,000, how many seconds would that be? 2 seconds. So you can choose how long you want the program to wait at a particular point. Okay? We also used a pair of commands that go together. They were do and loop. So what did these two commands do when we used them together? Yeah, right, it made a loop. It made it repeat this part of the program forever. So if we put our blinking commands inside of the loop, then it just makes it blink over and over and over again forever, right? So that's what we did last time. We used that. Oh, and then there was another kind of loop that we looked at, right? You guys remember the other kind of loop? Yeah, for next, exactly. So it was something like for counter equals 1 to 10, and then we had some code in the middle that we wanted to repeat, and then at the end we said next. So this, what does this for next command tell us to do, or tell the program to do?
Loop 10 times.
What's that?
Loop 10 times.
Yeah, repeat 10 times, loop 10 times, exactly. What happens is that this counter is something called a variable. This is a little spot that the computer uses to save a number, to remember a number. So what happens is that the first time that this loop runs, it puts the number 1 into this variable called counter. And then when it gets down to next, it comes up to the top, and then it adds 1 onto counter. So the next time the loop runs, counter is 2. And it comes back around and counter becomes 3, and so on. Until counter gets all the way up to 10, and then it stops. So that's how this for next loop works. There was one extra little wrinkle for this for next loop, right? Because we're using a variable, we need to tell the computer that we're going to use a variable before we actually use it. So that was a separate line up above. So there was this line that was counter var byte. So this command says that this thing is a variable, and then this tells the computer how big that variable is, how much memory it should use for this variable. So when we say byte, that means that the counter, it uses 1 byte of memory. That's 8 bits, which means that the counter can be any number between 0 and 255. Okay? So that's what's happening in a for loop, for next loop. So any questions about that? Okay. So that was a quick introduction to circuits and just a little bit about programming, just enough to get us started and get us so that we could actually build a circuit and make it do something cool, right? So any questions about that?
How many bytes can it go up to?
How many bytes can it?
240 or?
Oh, so 1 byte is enough memory to store any number between 0 and 255. Yeah.
This command tells us how many bytes you use, or it specified the counter variable byte.
So
This
we specify that the counter, the size of the counter, is 1 byte. Yeah.
which is okay.
Yeah. Other questions? Yeah.
Can we put something else, not byte?
Yes, there are other sizes that you could put. I don't know them off the top of my head. I think there are things like word or long or other things like that. We can look them up in the book. But if you choose different options here, you can choose different amounts of memory and therefore different maximum values for counter. Yeah. So in this case, we know that we're only going up to 10, so 255 is plenty big. But in other cases, you might be running the loop, 500 or 1,000 times, in which case you would need a bigger chunk of memory to store the number. Yeah.
So in our case, it's only 255 it has. But
In our case, it can only go up to 255 for this program. Yeah. If we needed more, we would have to choose a different size here. Yeah. Other questions? Okay. Cool. So that was what we learned last time. This time, we're going to build on that a little bit. We're going to have a similar circuit to what we built last time, but we're going to make it create Morse code. Have you guys ever heard of Morse code before? Yeah. for those of you who haven't heard of it, it's a way of sending messages using just dots and dashes, short and long pulses. Okay. This is a very old technology. This was used back when telegraphs were the only way of communicating. So basically, what happens is that each letter in the alphabet is represented by a series of short or long pulses. And one person can create these short or long pulses, and somebody else can hear them on the other end of the line, and so you can send messages from one place to another. So we're going to do that today. We're going to actually teach our basic stamp how to create Morse code. And you guys are going to get to write your own names in Morse code and see them come out over be flashed on an LED. Okay, so you're all going to get to write short messages and see them come out in Morse code. Now again, we're not going to make you start from scratch. We're going to give you a program to start from, and you guys will just have to modify that and improve it. So we're going to give you a short message. You're going to have to lengthen it and put your own name in there. Okay? So let's see how that's going to work. Before we go on and talk specifically about the lab, though, I wanted to talk a little bit more about electricity. Okay? So we talked just briefly about electricity last time, but I wanted to go into it in a little bit more detail now. So give me just a second. So we're going to start by talking a little bit about what is electricity. Okay? And then we're going to talk about a few key terms. We're going to talk about voltage, amperage, resistance, and then the units for each one of these. Okay? And I'll also tell you a little bit about why units are so important. I really stress that everybody puts units on their tests, and if you don't put units on your test, I mark you down. And it's not just because I'm trying to be a jerk or trying to look for ways to take away points. It's because units are really important. So we'll talk about that when we get there. Okay? So first of all, let's start with a little bit about what is electricity. So I think I touched briefly on it last time. Really, we said that to understand what electricity is, you have to go down to a molecular level, right? So we said that, we talked about atoms, right? We said that an atom has a nucleus, which is the center of the atom, which is made up of protons and neutrons. The protons have positive charges, the neutrons have no charges. And then around the outside are these electrons. Exactly. And when you have a piece of metal or any other kind of matter, what you really have is a whole lot of these atoms packed closely together. And when you have a whole lot of these atoms packed closely together, it's possible for electrons to move from one atom to another. And that's really what electricity is. Electricity is the movement of electrons. Okay? Yes?
What, I don't say very closely, what causes electrons to, is that like from, because of power source is turned on?
Yes, exactly. Exactly. So the question was, what causes the electrons to move? And the answer is this force called voltage. So since that's one of our key terms, let's write that down. Voltage is the force that causes electrons to move. Now, that voltage can come from a lot of different places. It could come from a battery that's connected. It could come from a power supply. It could come from you walking across the floor with socks on. You could build up a voltage on yourself. It could come from a cloud that's built up enough charge in it, enough of a difference in voltage to create lightning from the cloud to the ground, or from the ground to the cloud, depending on what's going on. So voltage is the force that causes the electrons to move. Different materials, some materials hold on to the electrons more tightly than other materials. Some materials really don't want to let the electron jump from one atom to the next. So those materials are called insulators, because an insulator is something that doesn't allow electricity to flow very easily. Other materials, like metals, make it very easy for the electrons to go from one atom to the next. Those types of materials are called conductors, because they conduct the flow of electricity. So the property of the material determines whether it holds on to the electrons tightly or not, and therefore whether it conducts electricity or whether it insulates. Right? So another key term that I wanted to talk about was amperage, or current. These are two different names for the same thing. This is how much electricity is flowing. Okay? So if you have a lot of electricity flowing, then you have high amperage or high current. If you have a small amount of electricity flowing, that's low current or low amperage. And then finally, the last term I wanted to talk about here was resistance. Can you guys see this bottom line here? Yeah. So that is opposition to the flow of electricity. So we talked about conductors. Conductors make it easy for the electricity to flow, so they have low resistance. Metals have low resistance. Insulators make it hard for the electricity to flow, so they have a lot of opposition to the flow, therefore they have high resistance. Okay? And when we talk about little resistors, we said that the resistors can come in different values, and really the way that resistors are made is that the company who makes them takes two bowls of material. They take one bowl that's a good conductor, and they take one bowl that's a good insulator. And they pour them together, and they mix them all around, and then they put them into little packages. And that's how they make a resistor. If they want it to have more resistance, they pour in more of the insulator, right? And so there's less of the conductor, so it's harder for the electricity to flow. If they want less resistance, they just pour in more of the conductor and less of the insulator, and they mix them all together, and then it's easier for the electricity to flow through. So that's what resistance is. It's opposition to the flow of electricity. So questions about what electricity is, or what voltage or current or resistance are? Yeah.
Is there a specific amount of resistance that like defines this? If it's this resistant, it's a conductor. If it's this resistant, it's an insulator, or is it just a general term?
It's just a general term. So you could say something is a good conductor or a bad conductor. There's not a real specific limit, black and white. It's more of a gray area. Yeah. Yeah.
Question is about voltage.
Uh-huh.
So you said it moves with electrons, but for example, if you take electrolytes, when some electrons move from anode to cathode,
Mhm.
they cover coating with different material. So is that actually destroys the molecules, the quality of the material in which the electricity flows, or how it stays current if the electrons actually move? They just jumping from one to another without. Is it kind of circulation of those electrons, or it's actually charge goes through them? That's kind of my question.
So the power supply really is supplying electrons. And there are different ways that can happen. In a battery, what happens is that there's a chemical reaction that takes place. So the inside of a battery is made up of these plates of metal, usually, that are separated by some kind of an acid bath. And what happens is that the acid actually reacts with the metal and takes extra electrons from, or creates extra electrons that are free to move. And those extra electrons are the ones that flow around the circuit and come back to the other side. So in a battery, it's a chemical process that causes that to happen.
It's chemical, it's not physical.
Right, in a battery it's chemical. In a solar cell, what happens is that you've got light coming in and hitting the cell, and those light those light rays, the photons, come and they dislodge some electrons from one side of a piece of silicon and allow it to move around. So there are different ways of creating those extra electrons, but it doesn't generally destroy the conductor that it's in. The conductor just, what happens is that you get an extra electron, like from over here, that comes in, and this one comes in and bumps this one out of the way. So then this one jumps over and goes there, and then that one jumps over and goes there, and then this one jumps over and comes off the end. So
They replace each other?
yeah, they replace each other. Exactly.
So that's why the solar panels in the time start producing less and less electricity, because the material they use is actually get exhausted, right? Or it's just destroyed by sun, temperature and stuff.
I don't think that the material is being destroyed in a solar panel. I think that what's happening in a solar panel it's a little bit more complicated. It's moving from one side of a piece of silicon and ending up on the other side of the piece of silicon. And the sun rays dislodge it from the one side and cause it to move around and end up back on the other side. But yeah, I'm not exactly sure why they produce less power over time.
Might take all batteries some time. They just using the quality of producing or storing.
Right.
over
Well,
time.
batteries really do have this chemical reaction going on inside them. So batteries are using up this. They are degrading the material that's inside of them. So that's why a battery will run out of power and die after a certain amount of energy has been used. But I think that solar panels. Well, I know that solar panels work on a different type of process. So I don't think that they get used up.
Which is a different process.
Yeah. Yeah.
Then what about rechargeable batteries? How
So-
does that-
What happens with rechargeable batteries is that when you let them sit, the chemical reaction works one way and it creates free electrons and they can flow around the circuit and get used up. And then when you recharge them, it actually causes the chemical reaction to reverse and work in the opposite direction. So I'm not a chemist, I'm not 100% sure about exactly what reaction is going on, but I know that just sitting by itself, it works in one way, like it converts, I don't know, it converts the metal, it does one thing, and when you apply electricity to recharge it, it causes the chemical reaction to work in the opposite direction and charge up and store more energy. Yeah.
Could you describe again the different components of the battery? Like what? I kind of missed it, but you're drawing.
Right,
I'm
so
not sure.
again, this is just sort of a thumbnail sketch, but you've got plates of metal that are separated by some type of electrolyte. So the electrolyte is usually like an acid or some kind of gel that creates a chemical reaction with the metal and causes or frees up some electrons which can then flow through a circuit. Yeah. Other questions? Okay. So we talked a little bit about what electricity is. We said voltage is the force that causes it to move. Amperage is how much electricity is flowing, and resistance is the opposition to the flow. There is a fun little cartoon that I like to show at this point because I think it kind of sums it up neatly. Let's see if I can find it. So there we go. So the amperage, the current is the electricity that's flowing along. The voltage is the thing that's pushing the electricity through the circuit. And then the resistance is the thing which is making it difficult for the electricity to flow. Okay? So these are how voltage, current, and resistance are all related to each other. Okay? So let that one stick in your head for a while. Now, you'll notice that it doesn't say current and resistance up here. It says amps and ohms. Anybody know why that is or what those terms refer to?
Units?
What? Yes, exactly, units. Those are the units. Okay, so just like we we have units for distance like feet or inches or meters or miles. We have units for electrical quantities as well. And it's very, very important to use the correct units. Let me tell you why. This is not just an academic exercise. This is a really important thing with real world consequences. A few years ago, NASA worked together on a joint project with the European Space Agency, and they worked together to send a probe to Mars. And so this project took years and years, millions of dollars. They sent the probe up, it got all the way to Mars, and then when it tried to land, it ended up going too far, and instead of touching down gently, it hit the surface of the planet and buried itself before the parachute ever deployed. Anybody know why? Yeah.
You're using two separate rings or units.
That's exactly right. The two agencies did calculations for the landing. The only problem was that the Americans did it in standard units and the Europeans did it in international units. So somebody said, okay, the distance from orbit to the ground is 583. And the Americans said, great, that's 583 miles. The European agency said, great, 583 kilometers. And when they got it wrong, the result was that the whole project got completely smashed into the surface of Mars. Okay, so this is a real problem. If you don't write the units on the page, then chances are that somebody else who reads it is going to read it wrong. Imagine that you went over to your friend's house and you asked your friend, hey, I'm getting a little hungry, I want to run to the grocery store. How far away is it? And he said, oh, don't worry, it's not too far, it's only 5. Is that 5 blocks? 5 miles? 5 minutes in the car? What? Right? If you don't have the units, the number by itself is basically meaningless. Okay, so that's why I really, really harp on putting down the units. And we're going to be using all different kinds of units in this class. So we're going to be talking about amps, but we'll also be talking about milliamps and microamps. We're going to be talking about ohms, but we'll talk about kiloohms and mega ohms also. So if you just write down that the resistance is 275, I don't know if that's 275 ohms or kiloohms or mega ohms or gigaohms or whatever. So it's really, really important to write down the units, okay? So that's my soapbox. That's why I think that it's really important to write down the units, and that's why I will deduct points if you don't do it. Okay? It's not just because I'm trying to be tough on you, it's because it really does have real-world consequences, and so you need to learn how to do it and make sure that you do it every time. So the units here, the units of voltage are volts. Okay? The units of amperage or current are amps. Volts can be abbreviated with a V, a large V. Amps can be abbreviated with an uppercase A. And the unit for resistance is ohms. And this can be abbreviated with the Greek letter omega. Okay? So whenever you write down a voltage, make sure that you put down volts. Whenever you write a current, make sure you put down amps. Whenever you write resistance, make sure you put down ohms. Now, if we're dealing with very large or very small measurements, there are shorthand notations that we can use, such as milliamps or microamps, megaamps, gigaamps. We'll talk about those later on. Okay? So it'll be acceptable to write down, kilovolts or mega ohms or things like that, but just make sure that you write down the unit that you are actually using when you use that unit, okay? Any questions about that? Yeah.
So we'll just be using this to like identify like when drawing circuits, or what other situations would we need to be like using units?
Well, when you take a measurement, for instance. So if you are, say that you're working on a piece of equipment and you know that the equipment is supposed to be using between 5 and 6 amps. So oftentimes you will have to test that equipment and make sure that it's running correctly. So you might do a measurement and write down in a logbook, measured current was 5.5 amps or something like that. And then it would be okay. Or measured current was 7.8 amps, then you would know something was wrong. So taking measurements like that for working on equipment. Also, when you're doing experiments and things like that, you might have to measure the resistance of a certain piece of equipment, or measure how much voltage was coming out of a battery to check that the battery wasn't dead. So all of those are cases where you would need to write down volts, amps, or ohms, and the value associated with it. Yeah. Other questions? Okay. Cool. So we talked a little bit about these key terms. We talked about what units are, why they're so important, and which units are associated with current, voltage, and resistance. So let's go on and talk a little bit about today's lab. Okay? Today's lab has to do with Morse code, like I said. So let's pull up the lab and see what we're going to be doing. So like I mentioned earlier in the class, the goal of today's lab will be to create a message in Morse code. The message will be hi there, and then your first name. If there's two people in the group, you can choose one name or the other, or you can do both your names. It's up to you. Okay? So it'll be hi there Joe, for instance, or hi there Jordan. So we're going to see how we can actually do that. The first thing we're going to do is that we're going to build the same type of circuit that we built last year. Okay? So we're going to build that right on our breadboard, just like we did last time. I've got some extra components on here just holding in place. But you remember that the basic circuit that we built last time looked like this. We had a resistor going from pin 14 over to this row in the breadboard. Then we had an LED going from that row over to VSS. Remember, we needed the LED to be in the correct orientation, right? We needed the flat side of the case to be pointed towards VSS. Okay? So we're going to start by building that circuit on our breadboard. Last time, we wrote a program that made this light just blink on and off and always blink at the same rate. But this time, we're going to make it actually create some Morse code. So we actually have Morse code written out for you on the lab sheet. So the way that it works here is that a circle represents a short pulse of light, and a dash represents a long pulse of light. So the little circles are called dots, and the long rectangles are called dashes. So An A is a dot dash. So that would be a short pulse of light followed by a long pulse of light. Up here at the top, it talks about the timing for these. So it says a dash is equal to 3 dots. So if the dash was, I'm sorry, if the dot was 1/10 of a second, then the dash would be 3/10 of a second, right? The space between them, between parts of the same letter is equal to 1 dot, so, and so on. So you can figure out the exact timing for how long each one of these things should last, okay? So the goal of the lab is to write this message, hi there, and then your first name. So we're not going to throw you in at the deep end. We're going to give you a place to start from. If you come here to instructor files and ET302, and then I guess it's still under L01. Yeah. So there's this Morse code sample program. We can open that up. And I think that the Morse code starter is even better. Yeah, this gives you a little bit more to work with. Okay? So this has a whole bunch of these high pause, low pause, high pause, low pause, all these things going on over here. If we just had the commands, it would be pretty hard to understand what this program was doing, right? Fortunately, whoever wrote this program also put in the comments. So this is one example where you can see how much the comments really help. So at the top here, the comments say letter H. So that tells me right away that this part of the program is going to try and write out the letter H. Okay? So let's go back to our lab and see what the Morse code is supposed to be for the letter H. So the letter H is 3 dots, right? 3 short pulses of light. That's what we're supposed to get. Let's see what the program is doing. Did I say 3? It's 4, right? Yeah, I'm sorry. 4 dots, right? So the program here now has more comments. It says dot 1, and then a little farther on, dot 2, dot 3, and dot 4. So the program is telling us it's creating 4 dots in order to make the letter H. Right? So you can start to see how these comments really help us to understand what's going on, right? Okay. And then under each dot, it tells us how it's actually making that dot. So to make the dot, it says high 14, that turns the LED on, then a pause of 500, half a second delay, and then low 14 to turn the light off, and then a pause of 500. So another half second delay. So that's 1 dot, and then that gets repeated 3 more times to make 4 dots altogether to create the letter H. Any questions about how that works? Okay.
Would you be able to do just like 1 and then write, what was it?
Yeah, we're going to do a little bit of this together here. So
yeah, instead of doing 4 of them repeating, can you do the whole, you know how we combined the commands, which is the do and loop, was it? Yeah, do and loop and then 4 next. And use the counter to do that?
Yeah, that you could have done that. So this was just 4 dots, one after another. So instead of copying it and pasting it 4 times, you could have used a 4 next loop and made that run 4 times. So that would have been another way to do it. Yeah. There, in electronics and in programming, there are often many different ways to get the correct answer and to do the correct thing. So a 4 next loop would have been a very good way to do it also. Yeah, good point. Other questions? All right. When I'm programming, I like to give myself a couple of extra white spaces in between different chunks of the program, just so that when I'm reading it, I can tell where one part starts and the other part ends. It doesn't affect how the program actually works, it just makes it easier for me to read. And then if I'm copying and pasting parts of it, it makes it easier for me to remember where I need to copy and help me not copy the part that I don't want to copy. All right? So I've got the letter H up here, and then I put a little separation. And then we've got this line down here that says pause 1500. That's a 1.5 second delay between letters. Okay? So we've got the letter H, and then a delay between letters, and then now we've got the letter T. So let's go back to our lab. We see that the letter T is down here farther. The T is just one long dash. When we go back to our program, we see that the letter T is represented by just one long dash. Again, I'll give myself a few extra spaces here. So this part is the letter T, and then after that, there's this pause between words. Okay? So we know how to make an H, we know how to make a T, and we know how to make a delay between letters and a delay between words. So we've got all the building blocks that we're going to need. Now we just have to take those building blocks and add a few more things to make the message. So remember, the message that we're going to create is hi there and your name. So I've already got the letter H. I want to make the word hi. So I need to add the letter I, right? So let's do that together. What I'm going to do is I'm going to go here, give myself a few more spaces, and then I'm going to copy this. So this is where I start a new letter, but now it's not the letter H, now it's the letter I. So I'll put in the letter I. Now I'll go back to my lab and figure out what the Morse code is. So the letter I is just 2 dots. Okay? So if I go back to my program, I've already got a letter H that has 4 dots in it. What could I do to make the letter I? Yeah, I can just copy and paste the 2 dots that are already there. Oh, and before I do that, I realized that I put this part in the wrong place. I put it right after the other letter, but I should have had this delay in there. So I should have put this up there. All right. So, what's that?
Can you increase the size of the text?
Oh.
When you see the real?
Let me see if I can do that. I apologize, but I don't know how to do that.
I think if you hold control and scroll up maybe.
That's just scrolling in the window.
Push it bigger.
Yeah, to make the
Control plus, isn't it?
control.
Command.
No, it's not.
The font.
This is an older editor. I don't think it has a zooming function. I'm sorry about
Like,
that.
there's also an editor's preferences. At the bottom.
So, let's see. Oh, here we go. Editor font size. Hey, there we go. Thank you. All right. Is that better?
Much bigger.
Good, good. Okay. All right. So now we've got the letter H up here. We've got the delay between letters. We know that the letter I is represented by 2 dots. So we said we already know how to make 2 dots. We've done it before.
3 dots.
What's that?
3 dots.
The
Oh no, it's 2. I'm sorry.
Okay, no worries. So what we can do is we can copy the 2 dots that we already have. So I'll copy that, and then I will go down here and paste that. And now I've got my letter I. Okay? So now I've created the word high, right? I've got the letter H and the letter I. I'm going to start going on to the next word, which is T. But what do I need before I start doing the letters of the next word?
Okay.
Yeah, the delay between words. So now I can come up here and copy this and put that right in after the end of my first word before my next one. Okay? So then the next word starts with T. So you know how to do that. Then it would be H. We already have an H, so you could copy that whole thing and paste it in there. And so on. You can keep adding letters until you have the message hi there and your name. Okay? Yeah.
So T is just the long space. So how do you do the long space? There's no dots.
Right. So the instructions say that the dash is equal to the time of 3 dots. So each of our dots up here was lasting half a second. So the dash should last 1.5 seconds. So it should be a pulse of light that lasts 1.5 seconds. Down here we have the letter T, which is represented by a dash, and sure enough, we've got a pause of 1,500 milliseconds, which is 1.5 seconds. Okay. Other questions? Yeah.
Are you supposed to have both pauses there at the end of the hi? You have.
Oh, no, that's a good point. Thank you. When I copied this letter, I included this pause at the end. But you're right, that would be an extra pause that I don't need, so I should get rid of that. So, thank you for pointing that out. Yeah, other questions or comments? Yeah.
So each dot we have as half a second, and the delay between them is half a second.
Mm-hmm.
So for the dash, since that's 3 dots, would the pause between them still be just half a second?
Yeah, the pause is still the same length of time. Yeah. Other questions? Yeah.
It's not related to programming, but I was wondering what VDD and VSS stands for.
Right. It relates to transistors and special types of transistors called field effect transistors. Field effect you don't have to know this for tests or anything like that, just for your curiosity. Field effect transistors have 3 terminals. There's a gate, a drain, and a source. So they're abbreviated G, D, and S. If you are interested in the voltage at a particular terminal, it's abbreviated V, and then the letters, 2 of the letters of that terminal. So the voltage at the drain is VDD. The voltage at the source is VSS. So that's where it comes from. Mm-hmm. Incidentally, it's sort of counterintuitive. Normally you think about the drain being low and a source being high, like a drain into the ground. But with the MOSFETs, the drain is actually the high voltage and the source is the low voltage. So go figure. Yeah.
The third terminal was?
Gate.
Gate?
Yeah. Yeah. So we talk more about MOSFETs and other types of transistors in ET322, which is the next class after ET302. We get into a lot more detail. We'll talk a little bit about transistors at the very end of this semester. Yeah?
Just double check. So between each letter is 1.5 second pause, and between each word is 2.5 second pause.
I believe so. Let's see. So between 2 letters is, 3 dots or 1.5 seconds. Between 2 words is 5 dots. Exactly. You got it perfect. Mm-hmm. Yes?
Another similar question. How would you define breadboard?
How would I define a breadboard? It's I mean, you guys have seen what they are. They're these little, I guess a short definition would be a prototyping board that allows you to connect parts together without soldering. And there are many different variations on breadboards. So there are small ones, big ones, fancy ones, plain ones. We'll just be using, we'll use this one and one other model in this class. Yeah. Yeah. Okay. So, yeah.
Sorry. Would a breadboard be considered similar to like a regular circuit board?
So, right. So that's a good question. There are actually different kinds of breadboards. So the ones we're going to be using in this class are called solderless breadboards. Really, if you want to get technical about it, we often just call them breadboards. But it turns out there are other kinds of breadboards where you do use solder. So they have a similar hole pattern here, but they have lots of holes next to each other, but they are made out of the same material, the same fiberglass substrate as a circuit board. So those types of breadboards are more similar to circuit boards. When you are looking at a board like this, this is really generally called a printed circuit board. So this type of board has a circuit that's printed or etched onto the face of it. And so basically it's got lots of connections between different points that are made for you already. So with a breadboard, you're prototyping those connections and you can easily change them around, but they're sort of bulky and they stick out and they can easily be bumped and pulled out if you're not careful. A printed circuit board doesn't allow you the flexibility of changing parts around, but at the same time, on the other hand, it is a lot more durable, right? It's, if I can rub the surface of the circuit board and it's not going to change anything around, whereas if I just bump the circuit board a little bit, the breadboard a little bit, it can easily pull a component out. So circuit boards are ways of making connections between, so circuit boards are essentially permanent ways of making connections between components. Breadboards are temporary ways of prototyping connections between components. Okay? Yeah?
Do you see breadboards like that a lot in the real world, or are those mainly for education?
They're used quite a lot for prototyping. So if you're out in the real world and you're designing a new circuit and you want to see something, how something works, then you could use a breadboard. Or if you're just trying something out, you want to test one component and you have to build a simple circuit to test that out, you wouldn't go and design a printed circuit board and have that printed out. You would use a breadboard, something like that. You don't see breadboards used inside machines because the connections just aren't that stable, right? So if they were in a machine that was being used over time, they could vibrate a lot and components could fall out, or somebody could bump it and they could fall out. So they're used for prototyping and trying things out, but they're not used in production systems. Yeah. Other questions? Okay. Cool. So that is what I wanted to say about today's lab. I will take attendance and then I'll let you guys go.